get started. Oh, yeah, before we start, yes, so for the first time this semester, I was hoping to hold my office hours in a small conference room, like right down the hall. But yesterday, I kind of forgot about that, so I was holding them in my office, which is down the hall. So I don't know if any of you actually tried to come to my office hour in the conference room. If you did, I apologize. So I will try to remember to go to the conference room, because it's bigger, more roomy to hold more people. There are only a couple of weeks during the semester where that conference room is booked for job interviews. So during those 2 weeks, it's listed on the website. I'll be in my office, which is just down the hall on this floor. So during some of the discussions I've had with you, and during the very first lecture, the question came up about carbon as a semiconductor material. Right? So carbon nanotubes and graphene are a hot topic of research now for high-performance transistors. And so I just wanted to mention that in our department, every Friday afternoon at 1 o'clock, up on the 5th floor in this building, the Hogan Room, it's not too far from the elevators or from the main stairwell, we have a solid-state technology and devices seminar. So this Friday at 1 o'clock, actually 1:10, Professor Jeff Bokor, he's in our department. He's also one of the co-inventors of the 3D transistor here at Berkeley. He's going to give a seminar, and it's not designed for experts, but he's going to give a seminar on carbon, nanotube, and graphene transistors. So for those of you who are curious about that in detail, I'd encourage you to attend. Basically, these are open to the public, and I'm sure he'd be happy to see a lot of interest from the students in that subject. Yes, Ali? Pardon me? These seminars are not recorded. Yeah. I'm not sure. He might make the presentation slides available afterwards, though. Yeah. If there's enough interest, I can ask, and I'm sure he'd be happy to share them. Okay, but his group has done a lot of work on carbon nanotube transistors and graphene transistors. That's why he's going to talk about it. Okay. So let's get started with the lecture material for today. Let's see. We've covered some basic properties of semiconductors, right? So we learned about electrons and holes. Those are mobile charge carriers that can carry charge and therefore conduct current in a semiconductor material. And we can adjust the numbers of electrons and holes by doping as one way. And we can keep track of how carriers would tend to move in a semiconductor device by drawing an energy band diagram to see which direction carriers will tend to drift, and also with the Fermi level to keep track of carrier concentrations in different regions of the semiconductor. Okay, so we've learned how to do that. Now let's start to see how carriers move around in a semiconductor. This is how all electronic devices work. You have some electrons and holes flowing around. So in the lecture today, we'll talk about drift, which is the motion of a charged particle in response to an electric field that exerts a force on a charged particle. Next time, the topic that will be covered is diffusion. Okay, so that's another way that carriers can tend to flow and have net flow in one direction. And we'll also talk about generation and recombination. Generation is a process where electrons and holes are generated in pairs, and that can affect the concentration of carriers and therefore the conductivity. Recombination reduces the number of carriers, and that also therefore indirectly affects the conductivity, the drift, and the diffusion. Okay? All right, so let's look at mobile charge carriers in semiconductors. And okay, that's what I just mentioned. But so today we're going to focus on drift. And drift, for example, is important because it actually limits, I'm going to try to write more neatly, current flow in a MOSFET. So maybe you can guess from the name of a MOSFET, metal oxide semiconductor, that's describing the structure, field effect transistor. This is an electric field that's applied to cause current to flow. So in a MOSFET, when it's turned on, current is primarily flowing by drift. Okay? That's in contrast to a PN junction diode or a bipolar junction transistor, in which current flow is really limited by diffusion, okay, by spreading of carriers from one region of high concentration to another region of lower concentration. So just to summarize, diffusion limits current flow in junction diode and a bipolar junction transistor. Those are two ways that carriers can flow to conduct current in a semiconductor. Now, recombination and generation affect the concentration of carriers and or the gradient, concentration gradient of carriers. So that's how they can affect drift and diffusion current. Now, recombination is an important phenomenon for certain types of devices. This is a phenomenon that's leveraged in light emitting diodes. So certain types of semiconductor materials, compound semiconductor materials, when an electron and a hole meet up and they recombine, the energy given off by the electron when it moves from the conduction band to the valence band comes out as a photon. So that's, you can emit light. Generation is a phenomenon. What kind of a semiconductor device you think would leverage the phenomenon of generation? Solar cells, exactly. So we can actually generate electricity, generating electron-hole pairs to conduct current as a result of light shining on the solar cell. So we're going to basically cover all of these this week. So today, let's focus on drift. As I mentioned probably during my second lecture, an electron, let's just focus on an electron right now, which has a negative charge. When a force is exerted on an electron, let's say in vacuum, by an electric field, it will accelerate because the force is proportional to the charge on the electron times the electric field strength. And force is equal to mass times acceleration. That's in vacuum. So this is the free electron rest mass. In a semiconductor, because you have these atoms and they create a potential profile, a regular potential, electric potential for electrons within the crystal, they also accelerate, but they move with a slightly different mass than in a vacuum, and that's the effective mass. So if you see m star, that means that's an effective mass. M sub n, n stands for negatively charged particle, so that means for electrons. So m sub n star is the effective mass of an electron. Now, this effective mass, the actual numerical value for it is different than the effective mass that we use to calculate the effective density of states. Okay? So that's why we call it explicitly the conductivity effective mass. And as I mentioned last time, or earlier, it's just a matter of the effective masses are different in different directions, and the way you average them is different for determining conductivity versus the density of states, you know, how much the energy bands are separated, or so the energy levels within the bands are separated. Okay, so if we just take the equation from the previous slide, you know, F equals ma, and then just determine, okay, the acceleration as a result of electric field. You can get these simple equations for acceleration of electrons. Holes, similarly, it's just electrons moving in the opposite direction, but it's basically a hole moves with the ease because electrons move from covalent bond to half-filled covalent bond to half-filled covalent bond. And the effective mass of a hole, which is positively charged, so you have P here, is different than for electrons. So usually the effective mass, the conductivity effective mass for a hole is larger than a conductivity effective mass for electrons. That means a hole will, it's harder to move a hole around in a crystal compared to an electron. And that's because, yeah, you have to move from one covalent bond to another rather than just freely throughout the lattice. Okay? So in this class, please use these numbers for the conductivity effective masses for electrons and holes in silicon, and m naught is just 9.1 times 10 to the minus 31 kilograms. Okay, so a couple of lectures ago, Camille had asked, okay, how do you measure the effective mass, like in different directions? So let's say we have a semiconductor sample, and electrons are moving along the surface here. How do we sort of calculate the average effective mass along that plane? Well, one way to measure the effective mass, and this is documented in Professor Chen-Ming Hu's book that you have the link to online, is using the cyclotron resonance technique. And so basically you have a magnetic field, okay, the B is the magnetic flux density that you can adjust. So you apply an electric field normal to the surface of the semiconductor, and that will cause electrons, which are randomly moving in the semiconductor, to start moving kind of in a circular motion, perpendicular to that vertically oriented magnetic field. And the centripetal force, which is mv squared over r, r is the radius. Okay, so r, did I say that? Maybe not. So r is the radius of the circle in which the electron is cycling around like this. So mv squared over r, due to the centripetal force is going to exactly balance the Lorentzian force induced by that magnetic field. So then you can actually calculate an equation, rearrange this equation to get an expression for the velocity at which the electron is moving around in a circle as a function of the magnetic field. And the frequency, so basically how many times it goes around in a circle, you just take the velocity divided by the circumference, right? It's 2 pi r. And you get an equation that's independent of v and r. It's just the magnetic field flux strength and the effective mass. Okay? So then the key is that you apply a microwave electric field, okay, a circulating electric field like this. And the electrons, if that electric field that you apply is cycling, has the same frequency as the cyclotron resonance frequency, then the semiconductor will actually absorb more of that microwave energy. So you can keep track, you can detect how much energy is being absorbed, and the energy at which the peak amount of energy is absorbed is the cyclotron resonance frequency. Okay, so you can either change the frequency of the microwave until you see a peak in the absorption, or you can fix the microwave energy frequency and change the strength of the magnetic field to see where you see a peak absorption, and that'll give you the effective electron mass. How long ago was this technique developed? I don't know. I mean, it was pretty long ago. I'm just curious. Why do you ask? I mean, it is an old technique. So that's why, actually, I wanted to point out that a more modern technique that's used nowadays to more precisely calculate effective mass in different directions, crystalline directions, is angle-resolved photoemission spectroscopy. So you shine a laser of a single wavelength, of course, onto the surface of the semiconductor, and you look at the energy of electrons, kinetic energy of electrons that are emitted, and depending on the angle, okay, because the angle will tell you sort of the crystalline direction, the momentum, crystalline momentum. Actually, from that you can deduce this is kind of like the photoelectric effect a little bit. So you can deduce as a function of the angle, in other words, the direction in the crystal plane, the energy that the electron must have had in the semiconductor for different directions in the crystal. And from that, you can actually obtain the energy as a function of momentum. Okay, so let me just mention that a more recent technique. Okay, another technique is, I'm just going to write it in the corner here. So you have angle resolved photo emission, right? So it's light-induced emission of electrons. Spectroscopy. So you can tell the energy of the emitted electrons, and it's dependent on the angle, right? So that actually gives you energy versus momentum, and that's actually that's the crystal. So K is the wave vector of the electrons. So E versus K, but H bar K is the crystal momentum of an electron. So fundamentally, you get E versus K from the angle-resolved actually it's photoelectron spectroscopy, right? And then from that, what you get, so you plot E, energy versus momentum. If it's a normal particle, you will see something like a parabola, right? Because the kinetic energy increases with the momentum squared. So you get a parabola from this angle-resolved photoelectron spectroscopy. And you can derive it yourself, but basically m star is equal to the inverse of the derivative. So d squared E dk squared. So, and there's actually h bar here because momentum is proportional to, is actually h bar times k. Okay, so what this means is that as you increase the momentum, the kinetic energy, if kinetic energy increases more quickly, that means you have less effective mass. Does that make sense, right? So that's why, no, sorry, is that right? That's right. That's right. So so the steeper the slope, the lower the effective mass, right? So you can increase the kinetic energy faster if you have, with momentum, if you have lower effective mass. Okay, so this is the modern way to determine the effective mass in different directions in a semiconductor. Pardon me? Which bands? So generally, so this is technically for the valence bands, but people, I mean, well, it's the conduction band, conduction and valence bands. People can do this. Yeah, and you can read about it. I mean, there's lots of articles published on this now. But yeah, so just to answer that question, there are more modern techniques to get the effective mass.
So does the effective mass change if you're in a different direction?
Yes, so that's why the question was, does the effective mass change with crystalline direction? It does, right? Because the atomic densities are different in different directions. The bond orientation and the bond densities are different also. So electron and hole mobilities are different in different crystalline directions. And that's why the angle-resolved photo emission spectroscopy is actually more accurate, more precise, to get an entire energy versus momentum band structure for any material. Yes?
Why is there double side?
Arsenide. Oh, okay. Why is there a difference in the effective mass?
Yeah.
Okay, so the question is fundamentally, why is the effective mass of an electron much lighter in gallium arsenide than in silicon? Well, okay, so your question was regarding the effective masses. Oh, sorry. So that was on this. Okay, so the question is here. Why is, for gallium arsenide, why is that number so low, and why is it so different than holes? Yeah. Okay. All right. Do you want to venture a guess? Okay. So gallium arsenide, gallium and arsenide are larger atoms, more nuclear, core shell charge, and electrons are the outermost, the valence electrons are farther away, so they're probably just easier to move around in a gallium arsenide crystal. Gallium arsenide has a larger band gap, so that means the covalent bonds are stronger, so it's probably harder to move an electron, from one, to get an electron out of a covalent bond to move to a half-filled covalent bond. You can think of it qualitatively that way. So it's just harder to move holes around compared to silicon because you have stronger covalent bonds. And the size and it's like a larger outer shell. I mean, it's not 3s and 3p. It's like, higher maybe, right? They are larger atoms, so the electrons are on the average farther away from the core. So I think it's just easier for them to move around and then you have more core, like positive charge in the nucleus to help pull them along, right? It's like surfing throughout the crystalline lattice. So they just surf more easily in gallium arsenide compared to silicon. Okay, that's just qualitatively. Okay, a good question though. If I come up with a more detailed answer, I'll give it in the next lecture. Okay, so how do electrons move actually when you have an electric field applied to a semiconductor? So let me show you a video. Remember I asked you about pachinko on the first lecture? Okay, so this ball represents an electron moving through a lattice. So obviously there's an electric field equivalent being, there's a potential field here, right? There's gravity pulling that ball down. But the ball doesn't just drop straight down, it scatters around, right? Off these ballers, these pins. And that's similar to what happens in a semiconductor with electrons. Basically, you have these atoms that are vibrating about their average position. Okay, so the atoms at the silicon lattice are always in random motion, and the electrons have some kinetic energy. They're always moving around randomly. So they're just constantly scattering, and not necessarily hitting physically anything, but basically their electrons are moving and having their paths deflected due to motion of atoms, or if they encounter an ion, a dopant ion, they'll get a Coulombic force changing their trajectory. Okay, so this is what we call scattering. Okay, so electrons that get influenced by a vibration of the lattice, that's called lattice scattering, or phonon scattering. Okay, and the higher the temperature of the semiconductor, the more serious or more severe the scattering is, and that limits the ease with which an electron can just drift through a semiconductor. As I mentioned, if we have occasionally some some impurity atoms due to ionized dopants, then that can exert Coulombic force, okay, and that can be significant at very high doping concentrations. And finally, if you have a lot of electrons and holes around, an electron, if they come close to another electron, they can repel each other. So you can have carrier-carrier scattering, but that's only significant if you have very heavily doped semiconductor with very high, and as a result, very high carrier concentrations. Unless you're applying an electric field, there's no net current flowing ever in a semiconductor sample if you don't apply an electric field to it. Okay? So normally you have an electron that's moving around, okay, but there's no net current flow. That's basically the idea. Okay, so the question is, on average, what is that thermal velocity? What is the average velocity at which electron moves around in between collisions? Or how fast can it get? Well, if we take into account that there's 3 degrees of freedom, and on the average is 1/2 kT per degree of freedom, then it's 3 kT of energy for an electron. And, sorry, 3/2 kT. I did say kT over 2, I hope. Okay, so for each degree of freedom, you have 1/2 kT of energy on the average. And so you have 3/2 kT for a 3-dimensional crystal. And if we equate that to the kinetic energy due to thermal motion, random thermal motion, then we can actually solve to find the thermal velocity. And we find it's on the order of 10 to the 7 centimeters per second. So remember, the units are centimeters per second, so it's much slower than the speed of light. But this is also another number to keep in mind, order of magnitude. Just remember 10 to the 7 centimeters per second. Okay, what about for holes? So this is for electrons. So for holes, the only difference is the conductivity effective mass. Okay, so the only difference is that MP star is equal to 0.39 m naught, rather than 0.26 m naught. Okay, so this is an example of how you should do homework and exam questions. So the thermal velocity for holes, so those are positively charged. Let's call this negatively charged electrons. So thermal velocity for holes is just going to be equal to the thermal velocity for electrons, but just multiplied by the square root of 0.26 divided by the square root of 0.39, right? Because the mass dependence is in the denominator underneath the square root. So that's just the relatively quicker way to calculate this. So you don't have to plug in all these numbers and calculate them again. So it's about 1.9 times 10 to the 7 centimeters per second. But it's still on the order of 10 to the 7 centimeters per second. Okay? All right, so what we'll find is that on average then, when you apply an electric field to a semiconductor, the electrons will drift at much slower than this velocity, okay? I mean, they cannot drift faster than this. They'll be bumping into, scattering about. So if you're doing homework and if I'm asking you to calculate the drift velocity, if you get an answer larger than that, there's something wrong with your calculations. Okay, so let's see how the picture changes when you apply an electric field, okay? Basically, you still have a lot of scattering, but because of electrostatic force applied to this electron, which has minus q charge, the electric field is pointing to the right, then the force on the electron is to the left. And so on average, the electron will be sort of moving to the left, just like those pachinko balls were on average coming down, right, falling to the ground. Okay, so that results in net current. And what happens at each scattering event? The electron loses its kinetic energy, right? It loses it to the lattice. So that's why when you flow current through anything like a semiconductor or a wire, it heats up, right? You're dissipating power. Okay, so because of this scattering, the electrons don't undergo constant acceleration, but you can sort of model it as a quasi-classical particle moving at an average drift velocity. So let's just ignore the fact for now that electrons are actually moving in random directions and accelerating, decelerating upon scattering, and accelerating again, decelerating. I mean, let's just say on average, how fast is it moving to the left? Okay, that's the drift velocity, and the drift velocity is defined. Let's say for an electron, V sub d, and n for electron, negatively charged, is defined. Well, this is the definition of mobility. Okay, so the drift velocity will be proportional to electric field strength, so that hopefully makes sense, right? The higher the force, the faster the average rate at which electrons drifting. And that proportionality factor is defined to be the mobility. Okay, that's the field effect. That's the effective mobility. And N stands for electrons. P will be for holes. Okay, so let's go back to the later when we talk about extreme high electric fields. This will become important. But let's just practice visualizing carrier transport in an energy band diagram. Okay, so which direction is the electric field pointing in this energy band diagram? Well, first of all, let me just remind you. So if there's band bending, right, there's some slope to the bands. You know that an electric field exists. Just to remind you. And by the way, this is the same as valence band slope, right? Because they're equally spaced by constant amount. That's the band gap energy. Okay, so which direction is the electric field pointing in this energy band diagram? Left? Great. That's correct. So electric field is pointing to the left. And remember, electrons, this is a electron energy band diagram. So, and the conduction band edge represents the potential energy. So electrons will tend to float downhill. Go downhill, so they will tend to go to the right. So let's just draw an electron here, E, and minus for negatively charged. So it's going to be accelerated by the electric field, and it will encounter a scattering event. It'll lose its kinetic energy. Okay, so that's kind of represented by that down arrow. Then it'll get accelerated again. Maybe it'll go a longer distance before it gets scattered and loses its kinetic energy, and so on. So if you visualize drift in an energy band diagram on a microscopic scale, this is what's happening. But again, for convenience, we'll just say, okay, electrons moving to the right, following the conduction band edge at an average rate. Okay? So same thing, if you have holes moving in the valence band, if this is a p-type material, hole will be accelerated. It's positively charged, so electric field force will be positive in the positive E direction. So a hole will move to the left, loses kinetic energy when it gets scattered, and so on. That's how we visualize carrier drift on a microscopic scale for an energy band diagram. Okay, so maybe I forgot to update my slides, but in reality, later we're going to talk about velocity saturation. Do I not? Are there slides on velocity? Okay, sorry, I thought I had updated my slides, but okay, so let's talk about velocity saturation. It's pretty easy. So it's a drift velocity as a function of the electric field. Okay, so based on that equation, the definition of mobility, you expect a straight line, right? As you increase the strength of the electric field, the drift velocity will increase. And the slope is basically the mobility. But as I mentioned, there's no way that, well, there's always going to be some limit. And that limit is roughly on the order of 10 to the 7 centimeters per second. So once the velocity gets close, it actually saturates. Okay, so this is the saturation velocity. We'll come back to this later when we talk about MOSFETs, because in a modern day MOSFET, you have maybe 1 volt across a transistor that's like less than 100 nanometers long. And so electric field is pretty high, and so the velocity will be saturated. Okay, so this is usually referred to as the saturation electric field. And the saturation electric field actually depends on the mobility, right? So if you have, let's do an example here. You have a higher mobility material, like if you do something to enhance the mobility of electrons in your semiconductor sample, you'll have a steeper slope, right? But you still have the same ultimate limit in saturation velocity. So this electric field at which you reach the saturation velocity actually depends on your mobility. And typically it's in the range of about 10 to the 5 volts per centimeter. Okay? Oops. This is on the order of anywhere from 10 to the 4 to 10 to the 5 volts per centimeter. Can't just arbitrarily, apply a large field and expect the electrons to go faster and faster. There's a limit. Okay. Now let's derive an equation for the mobility. Okay. So just qualitatively, what do you think? What basic property? What do you think will determine the mobility of an electron? I guess the answers are on this page. Mean free path, that's true. So that's like the average distance between collisions or scattering events. That's right. And more directly is the scattering time, the average time between scattering events, right? So if you're scattering very frequently, then qualitatively you expect the mobility to be kind of poor. Right? So you want the average time between these scattering events to be long, to have higher mobility. Because you can accelerate, basically you can have your force, electric field, exerting a force, okay, minus Q times E, for a longer period of time before your electron is scattered. So it's the force times the time, that's the impulse. You want that to be maximum. Okay. The other thing that affects mobility is the mass, the effective mass. Right? The lighter the effective mass, the faster you will accelerate the electron, the higher the acceleration, the higher the average drift velocity. Okay. So it turns out then you can actually write a momentum conservation equation here, that the momentum gained or the momentum lost when you scatter an electron is equal to the momentum gained in between collisions. And Tm is the mean time between scattering events, and n just refers to electrons. Okay, so if you take into account conservation of momentum, you can actually then get an equation on this next slide for mobility. So mobility, okay, there's a Q in there for the charge, right? That's representing the amount of charge on an electron. So Q times tau, so the longer the time between collisions, the more mobile the electron, and the smaller the effective mass, the higher the mobility. So hopefully it's not too hard for you to remember this equation, tau over m, okay, defines the mobility, and there's a Q factor there. Okay, so you have a similar equation for holes, it's just that the effective mass of holes is used, and the mean free time between scattering events could be different for holes. Okay, question?
Mobility increases with temperature, right?
So the question is, how does mobility change with temperature? It actually depends. So we're going to cover that today. That's a good question. It depends on how heavily doped your semiconductor is. Okay? So so qualitatively, mobility depends on the mean time between, the average time between scattering events. So if you have a lot of dopants, the time between scattering events is shorter, but the dependence of that on temperature changes. But anyway, we'll cover that in a few minutes. Yes, question back there?
So hole is not really like this.
Okay, so that's a good question. What does it mean when a hole is physically scattering? Because hole is not a physical thing. Okay. Well, okay. A hole is covalently bonded electron moving from one bond to another, essentially. And if you have an electric field, electrons will actually want to go in one direction, so the hole moves in the other direction. So like if atoms are vibrating, then that will affect which covalent bond it prefers to go to. So it'll change direction. It's not going to move in a straight line, right? It's going to like sort of change directions depending on the vibration, or if it sees a dopant ion that's positively or negatively charged, it will tend to want to move in that direction or away from it. So in a sense, the path of electrons moving through covalent bonds is also affected by lattice vibrations and by Coulombic force. Okay, so it does still matter. Does that make sense? Right, so the question again was, why is the effective mass of a hole different, or usually larger than an electron? Because it's just easier for electrons to move in the conduction band, like throughout the lattice, rather than having to move from one covalent bond to another. That's basically it. Yeah, just like it's easier for me to walk through the room rather than for you to move, like by moving from one chair to another. It just takes, it's just harder. Right?
So
That's right.
tendency is, or what I think what he was asking was that
Yes, the mobility of holes is dependent on electrons in covalent bonds, which is different than the mobility of electrons that are free to move around. I mean, they're not forced to move from covalent bond to a covalent bond. Yeah, actually, this was a homework problem from in the past. But if you look at the this band, I don't know if any of you looked at this applet. Uh-oh, let's see if it works. But it's actually nice if you can see the bonds. Structure. Let's see if I can show. Okay, so you see these bonds. If you want to have an electron move from covalent bond to covalent bond, it's actually fastest to move right here along this line here, right? From one covalent bond to another, and that's the 110 direction. Actually, and that's the reason why hole mobility is highest in the 110 crystalline direction. But for electrons, it's faster to move for electrons to move sort of in this direction here, because you basically have the lowest density of atoms in the way, right? So electrons that are free from covalent bonds move differently than electrons that are that are forced to move from bond to bond. Okay? They're good questions. But it's good to make sure you understand that qualitatively right? What's going on? Okay, so these are the, at room temperature, electron and hole mobilities of various semiconductors. So silicon actually has pretty decent electron mobility. If this is for undoped semiconductor, the hole mobility is much, it's lower. And so that's one reason why people are starting to develop advanced semiconductor materials for higher mobilities of holes, for example, using germanium for p-channel transistors. And in the future, perhaps some indium gallium arsenide or gallium arsenide for an electron-based transistor conduction. We'll talk about that later when we talk about advanced transistors. Okay, so let's see what, so we have an idea of the thermal velocity. Let's see what's the typical drift velocity. Okay, so let's calculate the whole drift velocity for a sample that's undoped of silicon. Electric field is 1 kilovolt per centimeter. Okay, so let's see, is that realistic? Kilovolt per centimeter. Wow, these are fancy. Okay, it's kilovolts per centimeter. So typically, okay, as I mentioned, we have like 1 volt. Let's say typical in a transistor. We're going to talk about this later, but we have heavily doped N-type source and drain regions, P-type body. We apply a voltage to the gate to control current flowing between the source and drain regions. Okay. So does anybody have an idea? I think I mentioned on the first day, typically what size, what's the length of this channel region in between the source and drain? On the order of magnitude, you should have an idea. Okay, 10 nanometers, that's actually not bad. Okay, but yes, the most advanced technologies today is like 30 nanometers. But let's just say roughly 100 nanometers. And the maximum voltage applied to a transistor is on the order of, say, 1 volt. Okay, so what's that electric field strength? Just so you know. So it's 1 volt. So this is an example of how you're supposed to be able to convert units. 1 volt divided by 100 nanometers, so that's 100 times 10 to the minus 7 centimeters. Huh? Oh, okay, so we do, yes, yeah. So in this class, we kind of use centimeters for concentrations and electric fields and so on. So let's do that. Okay, so this is basically 10 to the 5th volts per centimeter. Right, so that's pretty high. So that's why I said in a typical MOSFET, we're looking at saturation velocity. But let's say we need to flow current in this transistor. Current flows in the channel, yes, that's true, but it also has to flow in these heavily doped regions. And the voltage drop, ideally, within the source and drain regions is pretty small, less than a 1/10 of a volt. So electric field, usually in the heavily doped region, if you're just trying to use semiconductor as a resistor to flow current through, which is basically these source and drain regions, electric field, because the voltage drop is much less in these regions compared to the channel, the electric field can be more like 10 to the 3 volts per centimeter. So this electric field strength is more relevant to, let's say, resistors, basically. Okay? Okay, so 2 parts to this question. What is the drift velocity? Okay, so let's do that quickly. Do I have the answer? Okay, maybe not. Okay, so the drift velocity mobility is 470, is that right? Yeah, 470 times 10 to the 3. Okay, so, I forgot to mention, sorry. The units. What are the units of mobility? Did I not write it? Oh, yes. Right, so pay attention. Centimeter squared. So remember, if we don't do meters here. Okay, centimeter squared per volt per second. Okay. All right, so it's 470 centimeters squared per volt per second times 10 to the 3 volts per centimeter. So the answer is in centimeters per second, and it's 4.7 times 10 to the 5 centimeters per second. Okay? So you should be able to do that kind of calculation on a quiz, I hope. Not too stressful. But it gives you an idea. So typically in a resistor, the velocity of an electron is on the order of 10 to the 5th. It's nowhere close to the saturation velocity. Okay, what is the average hole scattering time? So how much time is there between scattering events? This is an interesting exercise and too hard to calculate in your head probably. So the effective mass is 0.39 for holes, and the free electron rest mass 9.1 times 10 to the minus 31 kilograms. Mobility is 470 centimeters squared per volt per second. And let's see, 1.6 times 10 to the minus 19 coulombs. Now, this is where we suffer because we keep track of centimeters instead of meters. Okay, so that's why there's a conversion factor here that I have to put in. Hold on, sorry, my computer is too active. Okay. So it turns out if you look at this, this is 10 to the minus 9 kilograms centimeter squared per volt second per coulomb. But because of the conversion between meters and centimeters, there's a factor of 4, 10 to the 4 here, that in order to have this all divide out. So it's actually 10 to the minus 13 seconds, or 0.1 picoseconds. Okay, so it's less than a picosecond average time between collisions. So that's also good to keep in mind. In other words, it's scattering quite often, I mean, at a high frequency. Okay, so whenever you need to worry about this conversion factor, factor of 10 to the minus 10 to the 4, I will explicitly give it to you, like on the homework or on the exam. Okay. Okay, so mean time between scattering events is really short. How about the average distance traveled between collisions? So that's on the average, the thermal velocity times the mean time between scattering events. So it's 1.9 times 10 to the 7 centimeter per second. We calculated that on an earlier slide, times 10 to the minus 13 seconds. So this is about 19 nanometers. Yes. Question is, why is it thermal velocity rather than drift velocity? Because now we're talking about a micro scale. We're looking at how electrons or holes move from collision to collision, rather than on the average, like over many collisions, like how, on the average, how fast it's moving. So, so we're actually trying to see what's on average, how far does it travel from one collision to the next. So it has to be the thermal velocity. Okay. So, so somebody had mentioned 10 nanometers for a transistor length. Yes, so you're right. Actually, when the transistors are now getting towards this dimension, on order of 10 nanometers or so, we're going to start to see no scattering. And so some of you might have heard of ballistic transport. That's not because a transistor is like really mad or something. It just means that it's shooting without like hitting anything. Like, so it can actually travel from source to drain when you apply voltage and you turn on the gate without scattering once. And in that case, you can have the most current per unit time. I mean, sorry, the most charge per unit time, or in other words, the highest current flowing in a transistor. But it's good to sort of know, order of magnitude, the average scattering distance of carriers within a semiconductor. Okay, so now let's talk about the dominant carrier scattering mechanisms. As I said, there's vibrating lattice atoms, and there are impurity ions. Okay, and these contribute with different temperature dependence. Okay, so phonon scattering, hopefully, like intuitively, as you increase the temperature, the atoms are vibrating, more actively, and so you should expect decrease in the scattering time, right? Time between scattering events, so mobility should go down. And indeed, that's the case. Okay, so it turns out that the temperature dependence is T to the minus, very roughly, T to the minus 3/2. That's sort of theoretically the ideal. Okay, in reality, it's never like exactly ideal. Okay, so the mobility here is, remember, Q times tau over M. Okay, so M star, sorry. And so that's why it's proportional to the time. So the average time between scattering events, phonon scattering events, it's, let me see. Thermal velocity, remember, is we calculate on the previous slide is proportional to the square root of temperature, right? So bottom line is, as you increase the temperature, the time between scattering events goes down, and so the mobility goes down. Okay. What about impurity ion scattering? Okay, so what happens is if you have an electron flowing in your, or just moving around in your lattice, in the crystal, and it comes near to a boron ion that's negatively charged, it's going to get repelled. If it comes near an arsenic atom, it'll get attracted. So in any case, its path of motion will be affected. So we call that a scattering event. Okay? So that's what we call scattering. Okay, so if an electron is moving faster, in other words, at higher temperature, electrons on average, the thermal velocity goes up, right? So if an electron is moving faster, it will get affected less by this charge because it'll spend less time near it. Right? So it won't be deflected as easily if you heat up the semiconductor. It won't be deflected as easily by a charged atom or charged ion, obviously. Okay? So the temperature dependence is actually different than for the phonon scattering. As you increase temperature, the mobility improves because you have less influence of the scattering. Okay? Of course, the more ionized dopants you have around, the more scattering, the more likely you're going to scatter. So you have this in the denominator, right? The total dopant concentration, no matter if it's positively or negatively charged, they both degrade mobility. So you take the sum of the dopant concentrations and put it in the denominator. Does that make sense? Okay. So qualitatively, do you see that there's fundamentally a difference in the temperature dependence of these scattering mechanisms? Okay, so what happens when you have both scattering mechanisms that exist substantially in the semiconductor? Okay, so this is a probability. So you have to consider it this way. What is the probability that a carrier will experience scattering, whether or not it's due to a lattice vibration or an ionized dopant? Well, the probability is, okay, within a certain time frame, let's say dt, and you take dt divided by the average time between scattering events. That's the probability, like, okay, if you wait for full scattering time, then the probability is pretty much 100% that you will have, the electron will have experienced a scattering event. Right? So the probability is just going to be inversely proportional to the scattering time, the time between scattering events. Okay, but there are different types of scattering. Okay, so the average time between ion scattering could be different than the average time between phonon scattering events. So you have to keep track of those two different times separately, and you have to add those probabilities, right? So within a certain time frame dt, you have to add the probability that it will be scattered by any mechanism is just going to be equal to the sum of the probability of being scattered by every single one individually. Okay, so you're just adding probabilities here. So in other words, the real time between scattering events is you have to take into account the different scattering mechanisms, add the inverses, and take the inverse. Does that make sense? Because basically you're adding, what you're doing with this equation here to the left is you're just adding the probability that a carrier will be scattered. And then that's inversely proportional to the mobility. Right? So the higher the probability of scattering, the lower the mobility. Okay, so that's why when there's multiple scattering mechanisms present, you can separately say, okay, the mobility due to lattice scattering is, let's say, mu sub phonon. Mobility limited by impurity scattering is mu sub impurity. You add their inverses and take the inverse to get the actual total mobility resulting from all scattering mechanisms. Yes, Louis. Okay, so the question was, so tau phonon is related to temperature. That's correct, and the material, semiconductor material. And tau impurity, yes, that depends on the concentration of impurities. No, actually, it also depends on the temperature, right? Basically, because, yeah, it's because the thermal velocity increases with temperature. So a carrier is less susceptible to Coulombic scattering when it's moving faster. Okay? Yes, Ali. So the question is, at what temperature can you ignore phonon scattering? That's a complicated answer. So let me go over this first, because we will cover that in a subsequent slide. Okay, so mobility dependence on doping then. This is a standard plot that you should get used to using. So this is electron and hole mobility, two curves, as a function of the total, so this is very important, total dopant concentration. Okay? Not the net dopant concentration. That's what we use to calculate electron and hole concentration, right? Both positively charged and negatively charged ions reduce mobility. So what matters is the total dopant concentration when you care about mobilities. Okay, so this is interesting. Qualitatively, for very low dopant concentrations, let's say less than 10 to the 15 per centimeter cube, what do you think is the dominant scattering mechanism? This regime, phonon scattering, okay, so then that makes it easier this way. Okay, in this regime, what do you think it starts to become dominant? There's only one. Ionized impurities, right? So ionized impurities, the scattering due to that becomes dominant. So so basically the concentration of ions is so low here that it doesn't matter if you add more. It's like really the mobility is limited by the phonon scattering. And as you add above like 10 to the 15, then you start to degrade mobility because you have more probability of ionized impurity scattering. Okay. Now this is at room temperature, so I should qualify that. So this is at 300 Kelvin. Okay, so you see anything strange here? In this regime, the mobility is fairly constant. It doesn't depend too much on carrier concentration or the impurity concentration. So why do you think that's the case? Pardon me? Everything's already been ionized. Actually, okay, so at room temperature, we actually already assume all of the dopant atoms are ionized. So they all are negatively charged or positively charged and scattering as much as they normally would anyway. So that the concentration of ionized dopants does not change with dopant concentration. Okay, so that's not the explanation for the mobility leveling out. Electron-electron scattering. But if it's electron-electron scattering, then you would still see it go down, right? Because as you add more dopants, you have more electrons. But it's something to do with the electron concentration. Yes?
I was going to say, if you leave it more metallic,
Okay, so it's more like metal. Maybe, sort of. Technically, okay, so what we generally explain this to be due to is due to screening. Screening effect becomes so it might be similar to what you see in a metal. Okay, so does anybody know what screening is? Do we know what we're talking about? So I brought some screens, actually. You know, like to keep flies out of your window. Okay, so here's a screen, right? Can everybody see that? Okay, so let's imagine that you're doping the semiconductor more and more heavily. So let's say this is sort of a sea of electrons moving around, and you add more and more dopant. Okay? Okay, so I'm adding more and more. So eventually you have a whole bunch of electrons, and it's kind of like becoming hard to see. So let me demonstrate. Who wants to volunteer? Okay, Camille. Can you see what's written on the card? Yeah. Okay, so if I reduce the electron density, can you start to see?
A little bit. Okay.
Go Bears. Go Bears. Okay. All right. That's basically a screen effect, right? So basically, you dope it so heavily that there are electrons all over the place, and the electrons sort of from far away, you can't see the ions behind them. That's basically it. How about a Go Bears Berkeley engineering pen? All right. Thank you for your participation. Okay. So that's the screening effect. So at very high dopant concentrations, the mobility sort of just stay flat at pretty low values. But you see over this, you're changing the doping over orders of magnitude. The mobility, this is on a linear scale. So the mobility is changing maybe like a factor of 10. Okay? So this is why if you want to make semiconductor material very conductive, you just add a lot of impurities, the dopants. Yeah, that degrades mobility, but overall, you can conduct more current. So you have a lot more carriers, even though they're moving slightly, 10 times slower, you got thousands more. So overall, the semiconductor can conduct more current as you dope it more heavily. Okay, so to answer all these questions about mobility, well, it depends on, so the temperature dependence of your actual doped semiconductor, the mobility in your doped semiconductor will actually depend on your dopant concentration. Okay, so there's a couple of things to note in this plot. This is a plot of mobility now on a log scale, okay, so an exponential scale, as a function of temperature, again on an exponential scale. So just so you can see a wider range. Okay, so one thing to notice first is that if you have very lightly doped semiconductor, that's this upper line here, as you increase the temperature, mobility degrades. Okay, because it's just the only scattering, the dominant scattering is just due to las vibrations. So as you increase temperature, the las vibrations get more severe, and so you get degraded mobility. Now, when you start adding dopants, so now the carrier concentration goes up, and dopant concentration, impurity ions go up, you start to uniformly degrade mobility. Okay? But as I mentioned, if impurity scattering is dominant, then you actually should see that the mobility improves as you increase temperature. And so indeed, you do see that if you dope the semiconductor heavily enough so that at room temperature, which is right here, 300 Kelvin, right? At room temperature, you dope it so heavily that at room temperature, it's really strongly, the mobility is strongly limited by impurity scattering. Then as you change the temperature, yes, you can, if you lower the temperature, you'll start to see the mobility drop off because of more time spent near an ionized atom, and so it'll affect the mobility more. Okay, but so does that answer your question? Sort of, I mean, it's generally so most of the time for moderately doped or lightly doped semiconductor, as you increase the temperature above room temperature, the mobility goes down. So conductivity degrades. But for really heavily doped material, it can actually be the opposite. So it really depends on how heavily doped your semiconductor is. Right. Oh, I guess I put the slide here. Sorry. I knew I added it. OK. So this is actually measured mobility plot. I mean, so basically, how do we measure mobility? We plot the electron velocity or the hole velocity versus electric field. As I mentioned, in reality, we do see saturation around 10 to the 7 centimeters per second. Okay, so the mobility values are only valid at low electric fields. And as I mentioned, it's close to 10 to the 7 centimeters per second for electrons and holes in silicon. Okay? Okay, so finally, let's just work on deriving a simple expression for resistance. Okay, so if you have a bar of a semiconductor, what's the resistance to current flow of that bar? In other words, when you apply a voltage across the ends of the bar, how much current flows. Okay, so we can derive this expression pretty straightforwardly, I think. Let's consider because holes are positively charged. Let's just look at hole drift as a in response to an electric field. Okay, so this is an imaginary semiconductor, piece of semiconductor with holes that are flowing through it, drifting. Okay, this is drift velocity. So if you have an electric field, the volume from which, okay, so all the holes located in a volume, like the drift velocity times the delta t times the area, the cross-sectional area, all of the holes in that volume will cross that plane in a time delta t. Okay? So then the number of holes crossing the plane in time t is just equal to the volume times the density of holes, like holes per unit volume, right? So that's why it's p times the drift velocity times delta t times the cross-sectional area. What? Oh, okay, now current is charge, right? So you multiply by charge on a hole, so it's q times that. And then you divide, so current is just charge, total charge per unit time, so you just divide by delta t. So basically, you have a simple expression. Hopefully, it's not too difficult to see that if you want to increase the hole current, you can increase the number of holes, the concentration of holes. You can increase the velocity of holes if you want to increase the amount of charge per unit time. And you can increase the cross-sectional area through which the charge flows. Okay? A lot of times in this class, we'll talk about current per unit area, per cross-sectional area, because a lot of our devices like diodes and so on, you can make them large in cross-section or small, and basically the current will scale with the area. What's more important or more interesting is just to keep track of the current per unit area, so that's the current density. Okay? So the symbol used for current density is J rather than I. And the subscript is P for positively charged mobile carriers. And we explicitly talk about drift current today. Next time, we'll talk about diffusion current. Okay, so just remember then, the key thing to remember is that the drift current is proportional to the carrier concentration and the velocity. Okay? That's different than diffusion, which you're going to talk about next time. Okay, so when we apply a voltage across the semiconductor, we induce an electric field and some current flows. So we know that the velocity is proportional to electric field. Right? So this is the drift velocity, v d sub p. And for electrons, the electrons move in the opposite direction of the electric field, but they're negatively charged. So overall, if you apply an electric field, you have current flowing due to electrons and holes, and the current is always in the same direction for electrons and holes. So that's why you just simply add these two terms to find the total current flowing as a result of electric field applied. And by definition, sigma, the conductivity sigma, is defined by this equation. Basically, it's when you apply an electric field, you'll end up with some current density, and sigma is defined to be that proportionality ratio. Right? So sigma is defined to be J over E. So if you have a semiconductor, you'll have typically holes and electrons, and the conductivity is due to both of those mobile carriers. Resistivity, rho, is defined to be just the inverse of conductivity. That's it. So the units that we use in this class are ohm, centimeter. Okay, so in the very first lecture when I mentioned, for a semiconductor, the resistivity is like 10 to the 4 ohm centimeters. For metals, it's like micro ohm centimeters, and for dielectrics, it's like 10 to the 14 ohm centimeters. That's the units those are the units we use. Okay, so how does resistivity depend on doping? This is a plot from a textbook. So this is showing resistivity, rho, in ohm centimeter, as a function of doping. So this is on a log scale, log scale. So because typically we can control the dopant concentration over many orders of magnitude, and we can control the resistivity over orders of magnitude. Remember I said it was from 10 to the 4 to 10 to the minus 4? So you can have like 8 orders of magnitude change in doping, and roughly 8 orders of magnitude, or 7 orders of magnitude change in resistivity. Okay? Now, looking at the equation for resistivity, okay, if you look at this, so remember, typically when we dope a semiconductor, what's the atypical dopant concentration? What's the range? The 20, okay, that's pretty high. 10 to the 15, okay, that's good, that's fine, that's low, moderate. Okay, so 10 to the 15, so let's say we dope it 10 to the 15 donors. So that would mean we'll have 10 to the 15 electrons. So how many holes are there? 10 to the 5, right? The product is 10 to the 20, Ni squared. Okay, so ordinarily when we have a doped semiconductor, one of these terms, so remember the difference in mobility between electrons and holes, right? Maybe the electrons have 2 times the hole mobility, something like that, you know, on the order of 2 times. Okay, so the difference in the hole and electron mobility is not that great. But the difference in majority and minority carrier concentration is orders of magnitude. Okay, so usually we only have to keep track, really, of one of these terms. So if it's doped with donors, we only have to care about N, because P is negligible compared to N. And if it's doped with acceptors, we only have to keep the term with P, because N is negligible. Okay, just to keep your calculations simple. Okay, so that's why for N-type material, you just simplify the equation. You don't have to keep track of so many numbers. And mobility, you don't have to worry about looking at mobility values for both electrons and holes. Okay, so N-type and P-type material, you really only have to keep track of the majority carrier concentration and the majority carrier mobility. Okay, so note, this plot does not apply to compensated material. So compensated material is material that's doped with both acceptors and donors. And compensated material is often encountered, let's say in a MOSFET. The way we make this device is we start with maybe a P-type semiconductor wafer, or part of a semiconductor wafer, and then we selectively introduce, let's say, arsenic in these regions to form the source and drain conductive regions. So basically, these source and drain regions have both heavily high dose of arsenic and some boron. Right? So it's very common for a semiconductor sample to have dopants of both types, donors and acceptors. And if you want to be precise, you shouldn't use this plot to look up the resistivity. You actually have to calculate it based on the mobility in this slide here, right? Because you have to take into account ND plus NA. So the total dopant concentration will determine your mobility. This plot here assumes that you only have one type of dopant, so that your mobility is not going to be degraded. You know, it's assuming you only have one type of dopant, and that dopant determines the majority carrier concentration, like holes for P-type, electrons for N-type. Okay, so just be careful. Don't just, if I ask in the homework, which I do, for the next homework assignment, like what's the resistivity, don't use this plot if it's doped with 2 types of dopants. Okay? Okay, so resistance, pretty simple. If you have a bar of a semiconductor material, you apply a voltage across it. How much current flows? Well, the ratio of the current to, well, voltage over current is defined to be the resistance of that piece of semiconductor. And it's going to depend on the resistivity, which determines how easily, how well the material can carry charge, or how quickly it can carry charge. It also depends on the length. The longer the length, the more overall resistance to current flow that the semiconductor presents. And then W times T, that's the width of the bar times the thickness. So that's the cross-sectional area. Right? So basically, the larger the cross-sectional area, the more current you can flow per unit time. The more current you can flow, and so the resistivity, resistance goes down. Okay, so units that we use for resistance in this class are just ohms. Okay, so it's just volt divided by amp. Okay, any questions? Okay, so let's end by doing a simple, well, hopefully it's a simple example. What is the resistivity of a silicon sample doped with 10 to the 16 boron? Okay, so first thing you should write is, okay, boron is an acceptor, 10 to the 16 per centimeter cubed. And since I didn't give you any other information, you can assume that the donor concentration is 0, that there's no donors. Okay, so then what is P? 10 to 16, great. Okay, and then what's N?